It begins with something so simple, almost childlike in its design. You have a source, let's say a little device that can fire off single atoms one by one, and you have a barrier in front of it with two impossibly thin slits cut into it, side by side. Now, the laws of the world we inhabit, the world we can touch and feel and understand, they dictate a very straightforward outcome. Each atom, like a minuscule grain of sand, will choose a path. It will go through one slit, or it will go through the other. And on a screen behind this barrier we should expect to find two neat little piles, two distinct clusters of marks where these atoms have landed. That would be the picture, wouldn't it? If the subatomic realm played by our rules, if its fabric were woven from the same coarse, predictable stuff as our tables and our houses and our planets. But the reality, the drama that unfolds on this microscopic stage, is something altogether staggering. It's something that makes the mind just stop. Because opening that second slit doesn't simply provide a new route for the atoms to take. No, it does something utterly inexplicable. It erases the atoms' tracks from places where they were confidently landing when only one slit was open. A paradoxical, bewildering disappearance. And what's more, any attempt, even the most delicate, the most subtle effort to peek, to find out which of the two paths a single atom has taken, it immediately, almost vindictively, snaps the picture back to a boring, predictable pattern. Two simple bands. It's as if the atom, caught red-handed in the act of performing its deepest secret, rushes to put on the disguise of an ordinary law-abiding particle. But take away that prying detector, avert the all-knowing gaze of the experimenter, and once again, a complex, multi-banded pattern emerges on the screen. Interference. It's as if each atom mystically split itself in two, travelled through both slits at the very same time, its wave-like nature splashing across both pathways, and then, having done so, it recombined with itself to create this incredible ripple on the canvas of probability. This isn't an illusionist's trick. It's not a flight of fancy. This is the double-slit experiment, and it shatters the very foundation of how we think about matter, about time, and about the act of observation itself. The explanation for this baffling behaviour, this profound challenge to common sense, lies at the very heart of one of the most powerful, most successful, and simultaneously most enigmatic theories in the entire history of human thought. You can feel its breath in every transistor, in every laser beam, in the very understanding of why the stars shine and why we are here to wonder at them. That theory is quantum mechanics. And it's so much more than just a collection of equations. It is the architect's blueprint for the universe at its most fundamental level. Without its insights, the technological landscape of the last century would be almost unrecognizably barren and primitive. The silicon chips that have become the nervous system of modern civilization, the lasers that pierce the darkness and heal our bodies, these are its children. The televisions that paint our living rooms with light, the computers that extend the reach of our minds, the microwave ovens, the mobile phones connecting continents, these everyday miracles that we so casually take for granted, they all owe their existence to this strange and wonderful theory. Quantum mechanics predicts and explains the behaviour of the tiniest building blocks of matter with an accuracy that is, quite frankly, almost frightening. Not just atoms, those miniature solar systems of the microcosm, but the subatomic particles they are made of, those elementary whirlpools of energy and mass. It grants us a profound, though not always intuitively comfortable, understanding of how these particles interact, how they weave themselves into the complex patterns that form the world we experience, the world we are a part of. And it's right here, at the crossroads of its unbelievable predictive power and our inability to fully grasp its meaning with our everyday minds, that the great paradox is born. How can a scientific theory be so triumphantly successful at explaining the countless hows and whys of the world's machinery, and yet remain so deeply mysterious, so defiantly weird? Most practicing physicists, the people who juggle its formulae and rules on a daily basis, they don't really perceive this as an insurmountable problem. The theory works, and it works flawlessly. It has unravelled the knots of innumerable natural phenomena. Its mathematical apparatus is polished to a brilliant sheen. It's logical and it's clear. And really, do we have any right to expect that nature, on the scale of these unimaginably tiny, almost ghostly atoms, should behave in any way that is familiar or predictable to us? Our daily experience, after all, is confined to a world of people and cars, trees and houses. The point isn't that quantum mechanics provides a distorted description of nature, but that nature itself, in its deepest manifestations, behaves in a way that is unusual, paradoxical, almost taunting. And if quantum mechanics provides us with the theoretical tools to understand everything we can observe, then we have no grounds to blame nature, or the theory, for our own intellectual shortcomings, for the limitations of an imagination forged in the macroscopic world. Some physicists even display an outright impatience with their colleagues, who still try to find a more visual, more intuitive interpretation of quantum reality. Their position is pragmatic to the extreme. Enough philosophizing, take the tools and calculate, predict the results of experiments. The search for an absolute understanding of what is fundamentally beyond experimental verification, in the usual sense, is a fruitless waste of time, an intellectual luxury that a working scientist cannot afford. And indeed, the standard or Copenhagen interpretation of quantum mechanics, the one that has been taught to physics students for decades, has even laid down strict rules and conditions that scientists must adhere to regarding the information they extract from nature in any given experiment. This might sound unnecessarily obscure, but it's important to grasp from the outset. Quantum mechanics is unlike any other theoretical concept created by human genius in the entire history of science. Even after 20 years spent in its embrace, trying to fathom its deepest meaning, it is perhaps impossible to ever fully come to terms with it. There are many interpretations, including the popular and somewhat cynical shut up and calculate approach, which allows many physicists to work effectively without being tormented by existential questions. But this story is not just about the philosophical depths and paradoxes of quantum mechanics. It is also about its triumphs, about its countless applications in our daily lives, in the past, the present, and most excitingly in the future. We are embarking on a breathtaking journey, from the misty peaks of philosophy and the dizzying depths of subatomic particle physics, through theories of higher dimensions and hidden realities, to the brightly lit technological world of today's lasers and microchips, and onwards, to tomorrow's even more amazing world of quantum magic, where the boundaries of the possible will be redrawn. To feel that primordial strangeness again, you don't need complex mathematical derivations or cumbersome apparatus. All you need to do is return to that very experiment with the two slits. It is so straightforward in its setup and so beautiful in its ability to lay bare the mysterious essence of quantum mechanics that it serves as the perfect starting point. It might seem like genuine wizardry, a magic show performed by nature itself. But there's no sleight of hand here, no hidden mirrors or secret mechanisms. A rational explanation, in the sense that we are accustomed to understanding that word, simply does not exist for the situation it describes. When we direct a beam of light at a screen with two narrow slits, a characteristic interference pattern appears on a second screen placed behind it, a rhythmic alternation of bright and dark bands. This phenomenon is easily explained if we accept that light behaves as a wave. Light waves, passing simultaneously through both slits, much like ripples on water from two dropped stones, spread out and overlap. Where the crests of the waves coincide, they reinforce each other, creating a bright band. Where the crest of one wave meets the trough of another, they cancel each other out, forming a dark band. This is classical wave optics. There are, it would seem, no mysteries here. Let's conduct a similar experiment, but this time, instead of light, we'll use ordinary sand. Grains of sand, these little particles of matter, falling through the two slits, will quite predictably form two separate, clearly defined piles on the screen below. Each grain of sand, obeying the laws of classical mechanics, passes either through one slit or the other. No waves, no interference. Everything is simple and understandable. And now, let us prepare to meet the unknown. Atoms take the stage. A special atomic gun, a precision instrument of the subatomic world, fires a beam of atoms at a screen with two extremely narrow slits, positioned very close to each other. A second screen is coated with a special luminescent layer, on which tiny ephemeral sparks flash at the points, where a single atom makes contact. Atoms are, without a doubt, the tiniest particles of matter, and following the logic of the previous experiment with sand, they should behave in a similar fashion. First, let's open only one slit. On the back screen, directly behind this slit, sparks appear, their distribution somewhat scattered. This slight blurring can be explained by some atoms possibly grazing the edges of the slit and being slightly deflected. Now, for the culminating moment, we open the second slit. Intuition and our experience with sand suggest that we should perceive two separate groups of sparks, two distinct bright spots. But reality once again laughs at our expectations. Instead of two predictable spots, a full-blown interference pattern emerges on the screen, identical to the one we observed in the experiment with light. The brightest area of the screen, against all logic, becomes its very centre, the one place where, according to particle theory, we wouldn't expect to find a single atom at all. Perhaps the atoms, as they fly past each other, are somehow secretly interacting, colliding in some special coordinated way, guiding one another to create this wave-like pattern. But even this hypothesis collapses when the experiment is conducted under even stricter conditions. The atoms are fired from the gun one by one. The next atom is launched only after the previous one has already left its flash on the screen, completely ruling out any possibility of them interacting in flight. And what do we experience? The number of sparks gradually increases, and where they accumulate most densely, the very same light and dark bands of the interference pattern slowly but inexorably emerge. This pattern cannot be the result of the collective behaviour of many atoms, so what on earth is going on? What makes this result particularly astonishing is the following observation. There are certain areas on the second screen where atoms confidently land when only one of the slits is open. It would be logical to assume that by opening the second slit, we provide the atoms with an additional route, and therefore increase the chances of them landing in these areas. However, when both slits are open, atoms stop landing there altogether. This means that if an atom really does pass through only one slit, it must somehow, in some incomprehensible way, know whether the second slit is open and adjust its behaviour accordingly. Each atom leaves the gun as a tiny, localized particle, and strikes the second screen also as a particle confirmed by a single flash. But in between, in the process of passing through the barrier with two slits, something mysterious happens to it, something that causes it to behave like an extended wave that is capable of splitting into two parts, passing simultaneously through both slits, and then interfering with itself on the other side of the first screen. How else can one explain how a single atom is aware of the existence of both slits? Let's try to delve deeper into this mystery, to peer up nature's sleeve, so to speak. We'll install a highly sensitive atom detector directly behind one of the slits. This detector, like a vigilant guard, will register every atom that passes through its slit. The results are both predictable and perplexing. The detector triggers from time to time, recording the passage of a whole atom, never just a part of one. The atoms that have chosen the path through the other, unobserved slit will leave their sparks on the second screen. But here's the astonishing part. As soon as we start observing one of the slits, the entire complex interference pattern on the back screen vanishes. In its place, only two bright, clearly defined spots of light appear, exactly opposite each of the slits. The atoms now behave precisely as we would have expected particles to, like the grains of sand in our previous experiment. The impression is that an atom behaves like a wave when left to its own devices, but as soon as we try to trace its path, it immediately corrects itself and exhibits exclusively particle-like behaviour. It's as if the atom possesses some kind of foresight, knowing in advance that we've set up an ambush and are waiting for it at one of the slits, and so it outsmarts us by remaining in the form of a localized particle. Perhaps the very presence of a massive detector somehow physically influences the behavior of the atoms? But this explanation also fails to stand up to scrutiny, because as soon as we switch the detector off, thereby depriving ourselves of the ability to know which slit each specific atom passes through, the interference pattern reappears on the second screen, as if by magic. The key factor determining the atom's behaviour turns out to be the very fact of our observation, our knowledge, or lack thereof, about its path. And this is not yet the limit of the strangeness. There are experiments known as delayed choice experiments, where the decision to observe is made at the very last moment. One can install a detector near one of the slits, but switch it on only after the atom has already passed through the slitted screen, but has not yet reached the detector itself. We can precisely calculate the atom's flight time by controlling its initial energy. It would seem that at this point it's too late for the atom to suddenly decide to behave like a localized particle that has passed through only one slit, because it has presumably already spread out as a wave and passed through both. But not so. Even in such delayed choice experiments, where the decision to observe is made after the choice of path event should have occurred, the interference pattern still disappears, giving way to two spots. So, what is this incredible phenomenon? Quantum mechanics offers a mathematical description of what we observe, but it does not provide an intuitively understandable explanation of what is happening behind the scenes when we are not looking. Physicists have had to grudgingly admit that there is no rational way out of this labyrinth of paradoxes in the sense we are used to. It is not the human device theory that is strange, but nature itself, which at the microscopic level insists on such a bizarre, almost irrational reality. The poet Robert Frost in his famous poem wrote, "Two roads diverged in a yellow wood, and sorry I could not travel both, and be one traveller, long I stood, and looked down one as far as I could." But quantum objects, these fundamental building blocks of the universe, behave entirely differently. A single atom faced with Frost's fork in the road can, without hesitation, choose both paths simultaneously. Atoms are not tormented by regrets about the choice made, because they are capable of exploring all possible options at the same time. They clearly follow the advice of the great American baseball player Yogi Berra, who once remarked, "When you come to a fork in the road, take it." This astonishing behaviour is a manifestation of a fundamental quantum phenomenon known as superposition. To picture this concept more vividly, imagine a skier who needs to get around a tree standing in his path. In our macroscopic world of trees and skiers, he will choose either the left or the right route. But in the quantum world, that skier could have gone around the tree on both sides at once. And this isn't just a beautiful metaphor. In the quantum realm, things like this really happen. Professors Marcus Arndt and Anton Zeilinger at the University of Vienna conducted a now classic experiment with fullerenes, large carbon molecules consisting of 60 or 70 atoms, C60 and C70, shaped like footballs and having a diameter of no more than 1/1,000,000th of a millimetre. Despite their relatively large size by atomic standards, these molecules are currently the largest objects for which the wave-like nature of matter has been convincingly demonstrated. When a beam of such fullerenes was passed through a diffraction grating with several slits, areas appeared on the detecting screen where no molecules landed at all. Astonishingly, opening additional holes in the barrier, instead of the expected increase in the number of registered particles in certain places, led to their decrease. Such behaviour is completely illogical for classical particles flying along definite trajectories, but is in perfect agreement with a model based on the wave nature of single molecules. The detector registered individual clicks corresponding to the impact of localized molecules, but as the data accumulated, a complex wave-like interference pattern gradually emerged on the screen, testifying to the fact that each molecule had simultaneously explored all available paths. So if the universe at its heart is so profoundly strange, where on earth did we get the idea that it was simple and predictable? Well, where did this astonishing intuition-defying science come from? There's a common myth that at the end of the 19th century, physicists with smug confidence believed that the grand edifice of physics was mostly complete. All the fundamental laws had been discovered, and all that remained was to tidy up a few details. In reality, by the close of the 19th century, such a vast number of unresolved questions and unexplained phenomena had accumulated in physics that the atmosphere was literally electric with the expectation of a breakthrough. Scientists couldn't even agree on such fundamental questions as whether matter was composed of indivisible atoms or was continuous and infinitely divisible. fierce debates raged about the applicability of Newton's mechanics to Maxwell's newly formulated theory of electromagnetism. Phenomena like the photoelectric effect, black-body radiation, the mysterious line spectra of light emitted by different elements, all awaited their explanation. The world was abuzz with the discoveries of mysterious X-rays in 1895, radioactivity in 1896, and finally, the electron in 1897. Physics was in a state of creative chaos, on the verge of great change. A second myth asserts that the German physicist Max Planck instantly sparked a revolution in 1900 by proposing his famous formula to describe blackbody radiation, and quantum theory was immediately born in all its glory. The reality was far more complex and dramatic. Quantum mechanics did not emerge from the insight of a single genius. Its development took almost 3 decades and required the combined efforts of the greatest minds of that time from all over the world. Planck, in an attempt to solve the long-standing problem of how heated objects radiate heat, the blackbody radiation problem, was forced to make a radical assumption. Energy is emitted and absorbed not continuously, but in discrete packets, which he called quanta. Planck himself initially treated his idea more as a convenient mathematical trick than as a profound truth about the workings of the world, and he didn't even immediately realize the full depth and revolutionary nature of his discovery. The energy of a single quantum of light, according to Planck, is directly proportional to its frequency, and the proportionality constant is the famous Planck's constant, denoted by the letter h and equal to approximately 6.63 times 10 to the power of minus 34 joule-seconds. This number, however infinitesimally small it may seem, is one of the fundamental constants of nature. If Planck's constant were equal to 0, no quantum behavior, with all its strangeness and wonders, would exist at all. The problem of black-body radiation was that classical theories could not correctly describe its spectrum. Wien's formula worked well for short wavelengths, but failed at long ones. Lord Rayleigh's theory, conversely, described the long wavelength part of the spectrum well, but predicted the so-called ultraviolet catastrophe, an infinitely large power of radiation at very short wavelengths, which clearly contradicted experiment. Planck, seeking to find a theoretical basis for Wien's empirical formula and drawing on Ludwig Boltzmann's statistical methods concerning the behavior of atomic oscillators, presented his revolutionary formula at a meeting of the Berlin Physical Society on the 14th of December 1900. He proposed that these hypothetical oscillators inside the black body could only emit or absorb energy in discrete portions, proportional to their frequency of oscillation. That is, energy is quantized. This was a radical departure from the then accepted electromagnetic theory of Maxwell, in which energy was considered a continuous quantity. It is important to note that Planck at that time did not claim that all energy in the universe consisted of quanta. He only suggested that the process of blackbody radiation occurs in portions. For the idea of energy quanta to be extended to light itself, the genius of Albert Einstein was required. In his miracle year, 1905, Albert Einstein, then a young and unknown employee of the Swiss Patent Office, published a series of papers, any one of which could have immortalized his name. In addition to the special theory of relativity and a paper explaining Brownian motion, thereby definitively proving the existence of atoms, Einstein presented a revolutionary explanation of the photoelectric effect. This effect, which consisted of electrons being ejected from the surface of a metal plate when illuminated with light, also baffled classical physics. 3 key oddities were observed. First, the energy of the ejected electrons depended not on the brightness, intensity, of the incident light, but on its frequency, or wavelength. Second, there was a certain minimum threshold frequency of light below which no electrons were emitted, no matter how high the light's intensity. And third, there was no observable time delay between the start of illumination and the ejection of electrons. They were emitted almost instantaneously. Einstein, boldly developing Planck's idea, proposed that light itself consists of discrete packets of energy, quanta, which later came to be called photons. According to his theory, each electron is knocked out of the metal surface by a single photon. The energy of this photon, in accordance with Planck's formula, depends on its frequency, which immediately explained the first oddity of the photoelectric effect. The threshold frequency corresponded to the minimum photon energy sufficient to tear an electron out of the metal. This explained the second oddity. And the instantaneous nature of the effect was explained by the fact that the electron did not have to accumulate energy from a continuous light wave. Instead, it received all the necessary energy at once as a result of a collision with a single photon. It was for this work, and not for the theory of relativity, that Einstein was awarded the Nobel Prize in Physics in 1921. Thus, a paradoxical situation arose. Young's double-slit experiment convincingly demonstrated that light behaves like a wave, while the photoelectric effect irrefutably proved that light consists of particles, photons. This dualism, where the same object exhibits both wave and particle properties, became one of the central mysteries and fundamental features of the quantum world. The next significant step in the development of quantum theory was taken by the young Danish physicist Niels Bohr. In 1912, he came to Manchester to work under the direction of Ernest Rutherford, who had shortly before proposed his planetary model of the atom, a tiny, dense, positively charged nucleus at the centre, with negatively charged electrons orbiting it. However, this model, while intuitively appealing, suffered from a serious internal contradiction. According to classical electrodynamics, an electron orbiting a nucleus should continuously radiate electromagnetic waves, lose energy, and, as a consequence, spiral very quickly, in about 1/1,000,000,000 of a second, into the nucleus. Atoms therefore should have been unstable, which clearly contradicted reality. Bohr, inspired by the ideas of Planck and Einstein on the quantization of energy, proposed that the energy of electrons in atoms is also quantized. This meant that electrons could not be in any arbitrary orbits, but only in strictly defined stationary orbits, each corresponding to its own discrete energy level. An electron could jump from one stationary orbit to another only by emitting or absorbing a photon whose energy was exactly equal to the difference in the energies of these orbits. This model of Bohr's brilliantly explained the stability of the atom and the origin of line spectra, the unique set of discrete frequencies of light emitted or absorbed by each chemical element. However, despite its triumph, Bohr's model was applicable only to the hydrogen atom and hydrogen-like ions, and could not explain the properties of more complex atoms. For that, a further deeper development of quantum theory was required, and this development was not long in coming. In 1924, a young French aristocrat, Prince Louis de Broglie, in his doctoral dissertation, put forward a bold and elegant hypothesis. If light, which was traditionally considered a wave, can under certain circumstances behave like a stream of particles, photons, then perhaps particles of matter, such as electrons, could in turn exhibit wave-like properties. De Broglie proposed that a certain matter wave could be associated with every material object, the wavelength of which is inversely proportional to its momentum and therefore its mass and velocity. The more massive and faster the particle, the shorter the length of the wave associated with it. For macroscopic objects that we deal with in everyday life, these matter waves are so short that they are impossible to detect. But for light particles like electrons, and even for whole atoms moving at low speeds, the de Broglie wavelengths become large enough for their wave properties to manifest in an experiment. The question arose, perhaps it is this elusive matter wave, associated with the atom, that somehow passes through both slits simultaneously in the famous double-slit experiment, while the atom particle itself passes through only one of them. In the classical Newtonian world, determinism reigned supreme. Knowing the exact initial position and velocity of every particle in the universe, as well as all the forces acting upon them, one could, at least in theory, calculate its state at any future moment in time. The future was predetermined. However, even in classical physics, chaos theory showed that for such a prediction, one would need to know the initial conditions with infinite precision, which is practically impossible. The quantum revolution brought with it an even more radical idea, fundamental indeterminism. The very concept of fate as a predetermined sequence of events turned out to be scientifically false. In the quantum world, at its most fundamental level, unpredictability reigns, an unpredictability that is not related to our ignorance, or the imperfection of our measuring instruments. It is a property of nature itself. We can only calculate the probabilities of various outcomes. A perfect example is the radioactive decay of atomic nuclei. Quantum mechanics allows us to accurately calculate the so-called half-life, the time it takes for half of the existing nuclei to decay, but it's fundamentally unable to predict the exact moment when any particular nucleus will decay. Knowing the half-life is meaningful only when applied to a statistically large ensemble of identical nuclei. One can calculate the probability of a nucleus decaying over a certain period of time, but no more than that. Albert Einstein, until the end of his life, could not come to terms with this probabilistic nature of quantum reality, which was expressed in his famous phrase, "God does not play dice." However, as subsequent decades of research and experimentation have shown, in this dispute Einstein was, it seems, mistaken. In classical physics, the motion of objects is described by Newton's equations, which allow for the prediction of their trajectories with high accuracy. However, in the microworld, these equations prove to be useless. The Austrian physicist Erwin Schrödinger, developing de Broglie's ideas about matter waves, in 1926 proposed a fundamental equation that describes not the motion of a particle as such, but the evolution in time of a certain mathematical entity called the wave function, denoted by the Greek letter sex, SI. The solution to Schrödinger's equation for a specific quantum system, for example an electron in an atom, is this wave function. It contains all possible information about the state of that system. However, unlike classical quantities, the wave function itself does not give us the exact value of, say, the particle's position in space at a given moment. Instead, it allows us to calculate only the probability of finding the particle at one point or another in space, if we were to conduct a corresponding measurement. To get this probability, one must square the amplitude, the modulus, of the wave function. Imagine an electron confined in a small box. At the initial moment, its wave function might be localized in one corner of the box. But over time, according to Schrödinger's equation, this wave function will spread out, blur, filling the entire volume of the box. We can no longer say exactly where the electron is, but we can identify regions where the probability of finding it is higher or lower. This situation can be illustrated by an analogy with the search for a robber in a large city. The police may not know his exact location, but based on the available information, they can create a probability map indicating the areas where he's most likely to be hiding or to commit the next crime. If the robber is eventually apprehended at a specific address, this probability map changes dramatically. Now he is definitely here, and not anywhere else. Similarly, if an electron is detected at a specific point as a result of a measurement, its wave function instantaneously collapses, localizing at that point, and the probability of finding it elsewhere becomes zero. But what happens to the electron when we're not looking at it, when we're not performing a measurement? Most physicists who adhere to the standard Copenhagen Interpretation of quantum mechanics believe that in this case, the electron does not exist as a classical particle with a precisely defined position. Its state is completely described by its wave function, which can be smeared out in space. It exists as a kind of potential cloud of possibilities. As soon as we make a measurement, we look. This wave function collapses, and the electron materializes at one specific point. This concept may seem absurd contrary to common sense. The wave function, in order to describe phenomena like interference, must possess wave-like properties. Moreover, it is a complex quantity, meaning that at each point in space it is described not by one, but by two numbers, a real and an imaginary part. Each of these parts is itself a wave, and the complete wave function is their combination, which gives it a complex, multifaceted structure. From the probabilistic nature of the wave function and its mathematical properties follows one of the most famous and fundamental consequences of quantum mechanics, Heisenberg's Uncertainty Principle. It states that we cannot simultaneously know the values of certain pairs of conjugate physical quantities for a quantum particle with arbitrarily high precision. The most famous example of such a pair is the particle's position and its momentum, which is related to its velocity. the more precisely we measure the position of a particle, the less certain its momentum becomes, and vice versa. This is not due to the imperfection of our measuring instruments or the fact that the act of measurement itself inevitably disturbs the particle, although this also occurs. The uncertainty principle is a fundamental property of nature itself, embedded in the mathematical structure of wave functions. If a particle's wave function is highly localized in coordinate space, which means a small uncertainty in its position, then its corresponding wave function in momentum space will be highly smeared out, which means a large uncertainty in momentum, and vice versa. Niels Bohr called this phenomenon the principle of complementarity. Such seemingly mutually exclusive aspects as precise position and precise momentum are complementary and necessary for a complete description of a quantum system. An example of the uncertainty principle manifesting in real systems can be found in so-called halo nuclei, where some neutrons or protons have a wave function that extends far beyond the main part of the nucleus, which is possible due to the very small uncertainty in their momentum. The period from 1925 to 1927 was a time of true revolution in quantum physics, much more profound than the one initiated by Planck. The old quantum theory of Bohr, despite its successes, could not describe the spectra of atoms more complex than hydrogen, and offered no understanding of the nature of quantization itself. Young physicists like Werner Heisenberg, Max Planck, and Pascal Jordan developed a completely new mathematical formalism known as matrix mechanics. It was based on representing physical quantities not as numbers, but as matrices, tables of numbers, and operated only on those quantities that could, in principle, be observed in an experiment, abandoning concepts like electron orbits. Almost simultaneously and independently, the Austrian physicist Erwin Schrödinger, developing Louis de Broglie's ideas on matter waves, proposed a different mathematical approach, wave mechanics, the central element of which was his famous wave equation. It was soon shown, notably by Paul Dirac and Wolfgang Pauli, that Heisenberg's matrix mechanics and Schrödinger's wave mechanics were mathematically equivalent. They were simply two different languages for describing the same quantum reality. How do these new, deeper ideas explain the fundamental strangeness of the quantum world? At the heart of all these explanations lies the concept of the wave function and its unique properties. One such property is the principle of superposition. It is not exclusively quantum, it is a general property of all waves. Two waves on the surface of water, when they meet, superimpose on each other, creating a complex resulting pattern that is their superposition. Similarly, light waves passing through two slits interfere due to superposition. It turns out that the wave functions of quantum systems can also exist in a state of superposition. This means that a quantum system, for example an electron, can simultaneously be in several different states. An electron can be moving both fast and slow at the same time. It can be spinning both clockwise and counterclockwise at the same time. It can even be in two or more different places at the same time. Of course, when we make a measurement, we always find the electron in only one specific state, with one speed, one direction of spin, in one place. However, the very possibility of existing in a superposition before the moment of measurement is key to understanding quantum phenomena. That very interference pattern in the double-slit experiment, which arises even when atoms or electrons are passed through the slits one by one, is a direct consequence of the fact that the wave function of each particle passes through both slits simultaneously, being in a superposition of two states, passed through the upper slit and passed through the lower slit. And these two parts of the wave function then interfere with each other. When an atom is fired from the atomic gun, its wave function may initially be quite well localized in space. However, as it moves towards the screen with the slits, this wave function, according to Schrödinger's equation, inevitably spreads out, blurs. Upon reaching the screen with the slits, this extended wave function splits into two parts, each passing through its own slit. It is important to understand that we are describing the evolution of a mathematical quantity here, not the behavior of a classical particle. On the other side of the slits, these two parts of the wave function again spread out and overlap. That is, they enter into superposition and interfere. By the time this resulting wave function reaches the second detecting screen, The distribution of its amplitude, and therefore the square of the amplitude, which is the probability of detection, is such that there are regions where the probability of the atom landing is high, the bright bands of interference, and regions where it's close to zero, the dark bands. Although each individual atom is registered on the screen at only one point, the statistical accumulation of many such impacts from identically prepared atoms forms the observed interference pattern. The wave function is not the atom itself. It is our most complete mathematical description of its behavior and its potential possibilities, especially at times when we are not observing it. But what if this probabilistic nature isn't the final word? What if it's just a signpost, pointing to a deeper, stranger reality that connects everything, everywhere, instantly? Even more vividly and strikingly, the principle of superposition is demonstrated in devices called quantum interferometers. In such a device, a single particle, a photon, electron, neutron, or even an atom, upon entry is directed at a so-called beam splitter, for example, a semi-transparent mirror for photons, which gives it the opportunity to choose one of two different spatial paths inside the instrument. According to quantum mechanics, the particle's wave function splits, and simultaneously follows both paths, even if these paths are physically separated by a significant distance, centimeters, meters, or theoretically even light years. These two paths are then brought back together and directed at another beam splitter, after which detectors are placed. If the particle really did travel both paths simultaneously, then interference between the two parts of its wave function will be observed at the output, which will lead to the particle being detected with high probability in only one of the detectors and almost never in the other. However, if we try to determine which of the two internal paths the particle took by placing a detector on one of them, the interference pattern at the output immediately disappears, and the particle will be equally likely to land in both output detectors. Moreover, sophisticated experiments with the so-called quantum eraser have been conducted, which have shown that the information about which path the particle took, which destroys the interference, can be erased even after the particle has seemingly already made its choice, and in this case the interference can be restored. It's as if the particle not only knows whether we are observing it now, but also foresees whether we will try to erase this information in the future. Another astonishing and fundamental feature of the quantum world is non-locality, which is closely related to a phenomenon known as quantum entanglement. Imagine two hypothetical dice that always show the same result when thrown. For example, both land on 6s, then both on 3s, and so on, even if one of them is on Earth and the other is on Pluto, and they are thrown simultaneously, taking into account the signal propagation time, so they cannot communicate the result to each other. Such behavior would hint at the existence of some kind of instantaneous connection between them, violating the principle of the finite speed of light. In the quantum world, similar, albeit more subtle, correlations do indeed exist. If two or more quantum particles interact with each other in a certain way, their states can become entangled. This means that they cease to be independent systems and are described by a single, common wave function, even if they subsequently fly apart over a huge distance. A measurement performed on one of the entangled particles, which determines its state, for example, the direction of its spin, instantaneously, faster than the speed of light, also determines the state of the other particle, regardless of the distance between them. This phenomenon, known as the EPR paradox after Einstein, Podolsky and Rosen, who first described it in 1935, was called spooky action at a distance by Einstein, who considered it proof of the incompleteness of quantum mechanics. He suggested that there must be some hidden variables that predetermine the measurement outcomes for both particles. However, in 1964, the Irish physicist John Bell derived a mathematical inequality, Bell's theorem, which showed that if such local hidden variables really exist, then the degree of correlation between the measurement results for entangled particles cannot exceed a certain limit. Numerous experiments, starting with the pioneering work of Alain Aspect and his colleagues in 1982, have convincingly demonstrated the violation of Bell's inequalities, thereby confirming the reality of quantum non-locality and the untenability of local hidden variable theories. Quantum mechanics is indeed non-local. There is even the astonishing idea of interaction-free measurements, based on quantum principles, a striking example of which is the Elitzer-Vaidman bomb testing thought experiment, or, in a more peaceful version, determining the authenticity of a diamond among fakes. Using a special type of interferometer, a Mach-Zehnder interferometer, one can construct a situation in which the presence or absence of an object, for example, a photon-absorbing real diamond, on one of the interferometer's paths affects the outcome of the interference, even if the photon that triggered the detector actually travelled along the other path and never interacted with that object directly. In some cases, one can say with certainty that the diamond is real, because it could have absorbed the photon if it had gone down its path, without destroying it, as the registered photon avoided encountering it. However, the deepest and still not fully resolved mystery of quantum mechanics remains the so-called measurement problem. Why do we never directly observe the wave function in the process of its evolution or superposition? Why does the very act of observation or measurement cause this wave function to instantaneously collapse into one of the possible definite states, with the choice of this state being probabilistic? Why does the interference pattern in the double-slit experiment disappear as soon as we try to find out which specific slit the atom passed through? This mysterious process, the collapse of the wave function, lies at the boundary between the quantum and classical worlds. The observation itself, even the most delicate, inevitably disturbs the quantum system. Heisenberg's gamma-ray microscope, a thought experiment in which an attempt is made to determine the position of an electron using a gamma-ray photon, clearly illustrates that the more precisely we want to know the position, the more we change the electron's momentum. But this is only part of the story. Schrödinger's equation, which describes the evolution of the wave function, is strictly deterministic. Probability and randomness come into play only at the moment of measurement. But where exactly is this elusive boundary between the quantum system, which obeys Schrödinger's equation, and the classical measuring instrument, which registers a specific result? After all, the measuring instrument itself is ultimately also composed of atoms and therefore should obey quantum laws. The famous thought experiment with Schrödinger's cat lays bare the full acuteness of this problem. A cat is placed in a closed box along with a radioactive atom and a mechanism that, upon the atom's decay, releases a poison that kills the cat. As long as the box is closed and we do not know whether the atom has decayed, it is, according to quantum mechanics, in a superposition of two states, decayed and not decayed. Since the cat's fate is rigidly linked, entangled with the state of the atom, the cat too must be in a superposition of two states, alive and dead simultaneously. Of course, as soon as we open the box we will find either a live cat or a dead one, never both at once. Proponents of the Copenhagen Interpretation would say that until the moment of measurement, opening the box, it is meaningless to talk about the definite state of the cat, whether it is alive or dead. It exists only as a potential possibility described by the wave function. But what if, instead of a cat, there is a human observer in the box? He would surely know whether he was conscious or not, regardless of whether anyone opens the box from the outside. The measurement problem thus breaks down into two key questions. First, why do we never observe macroscopic objects, like cats or measuring instruments, in a state of superposition of macroscopically distinguishable states? For example, simultaneously alive and dead, or simultaneously registered a signal and did not register. The answer to this question, at least in part, is provided by the concept of decoherence. When an isolated quantum system, like a single atom in a superposition state, interacts, becomes entangled, with a macroscopic environment, which consists of a huge number of particles, air molecules, atoms of the measuring device, etc. This fragile quantum coherence, the ability for superposition and interference, very quickly, almost instantaneously, leaks into the environment and is lost. The delicate superposition sort of dissolves into the vast number of degrees of freedom of the macroscopic environment, and we can no longer observe its explicit manifestations such as interference. This process of decoherence is real and has been experimentally confirmed in recent decades in experiments with mesoscopic systems, those on the border between the micro and macro worlds. For example, in the experiments of Serge Haroche's group in Paris, where the superposition of states of an electromagnetic field consisting of several photons decohered in times on the order of 1/10 of a millisecond. Decoherence explains why Schrödinger's cat, by the time the box is opened, will no longer be in a state of both alive and dead. This state would be destroyed too quickly due to interaction with the environment inside the box. However, decoherence does not solve the second, perhaps even deeper, question of the measurement problem. Even if decoherence eliminates unphysical superpositions, leaving only classical alternatives, for example, cat is alive or cat is dead, how exactly is one single observable outcome chosen from these remaining possible options during a specific measurement? Why, in one case, do we find a live cat, and in another, when repeating the experiment, a dead one, if the probabilities of both outcomes were, say, 50-50? Quantum mechanics remains fundamentally probabilistic, and this unpredictability of the result of a single measurement does not disappear. There are many different philosophical and scientific approaches to interpreting the deep meaning of quantum mechanics. The standard, or Copenhagen Interpretation, developed by Niels Bohr and Werner Heisenberg, is more of a pragmatic set of rules for performing calculations and relating them to measurement results than a full explanation of what is really happening. It does not answer the question of how an atom passes through two slits simultaneously, but declares the question itself meaningless, as it concerns reality in the absence of measurement. It postulates the collapse of the wave function upon measurement, but does not explain the mechanism of this collapse. In contrast, the de Broglie-Bohm interpretation, also known as the pilot wave theory, or hidden variable theory, suggests that quantum particles are always real, localized objects moving along definite trajectories under the guidance of a real physical pilot wave, the quantum potential, which is related to Schrödinger's wave function. In the double-slit experiment, the atom particle passes through one specific slit, but the pilot wave passes through both, creating an interference pattern that then influences the particle's trajectory. This theory is deterministic at a fundamental level but appears unpredictable due to our fundamental inability to know the initial conditions precisely, the particle's position within the wave packet. And it is explicitly non-local. A change in the wave function, and thus the quantum potential, at one point in space instantaneously affects it at all other points. A completely different approach is offered by the many worlds interpretation of Hugh Everett. According to it, no collapse of the wave function occurs. Instead, every time a quantum system faces a choice, for example, an atom passing through slits, the entire universe, including the observer, splits into multiple parallel realities, in each of which one of the possible outcomes is realized. Schrödinger's cat turns out to be alive in one universe and dead in another. We, as observers, also split and are aware of ourselves only in one of these branches. There are other interpretations as well. The statistical interpretation, quantum mechanics describes only ensembles of systems, not individual events. The transactional interpretation, which proposes an exchange of offer waves from the past to the future and confirmation waves from the future to the past, the consistent histories approach, and theories of objective or dynamical reduction, which postulate a spontaneous collapse of the wave function not related to measurement. Despite these deep philosophical debates about the nature of reality, quantum mechanics has had a revolutionary impact on our understanding of the structure of matter and has led to incredible technological progress. Recall the dawn of the atomic age, which began with the discovery of mysterious rays. X-rays by Wilhelm Röntgen, radioactivity by Henry Becquerel and the Curies, and finally the electron by J.J. Thomson. Ernest Rutherford, with his experiments on the scattering of alpha particles, discovered the atomic nucleus, and Niels Bohr was the first to apply early quantum ideas to explain the stability of the atom and its spectrum. However, a true and deep understanding of the structure of the atom came only with the development of full-blown quantum mechanics and the introduction of Schrödinger's wave function. It made it possible to explain the existence of electron clouds around the nucleus, to introduce quantum numbers characterizing the states of electrons, and thus to understand the chemical properties of elements and the structure of Mendeleev's periodic table. Another purely quantum property with no analogue in the classical world is the spin of elementary particles, a kind of internal angular momentum. The spin of an electron, for example, can only take two discrete values, up or down relative to a chosen direction, and explains phenomena such as the Zeeman effect, the splitting of atomic spectral lines in a magnetic field. Electrons, protons, neutrons, and the quarks that compose them are fermions, particles with half-integer spin, which obey the fundamental Pauli exclusion principle. Two identical fermions cannot occupy the same quantum state at the same time. This principle is the cornerstone of our understanding of the structure of atoms. It is what forces electrons to arrange themselves in different energy shells. The stability of matter, and even the properties of exotic objects like neutron stars. The particles that carry forces such as photons are bosons, particles with integer spin, and do not obey the Pauli principle. On the contrary, they like to be in the same state, which is the basis for the operation of the laser. Peering inside the atomic nucleus, physicists discovered that it consists of protons and neutrons, collectively called nucleons. These nucleons are held together by a powerful force called the strong nuclear interaction. In 1935, the Japanese physicist Hideki Yukawa proposed that this interaction is carried out by the exchange of special particles, pions. These pions are virtual particles. They are, as it were, borrowed from the vacuum for a very short time, permissible by the uncertainty principle for energy and time, and this borrowing of energy is possible thanks to Einstein's famous formula E=mc2, which links energy and mass. There is also the weak nuclear interaction, responsible for certain types of radioactive decay, such as beta decay, in which a neutron in the nucleus can turn into a proton, or vice versa, emitting an electron, or its antiparticle, a positron, and an elusive particle called a neutrino. The phenomenon of quantum tunneling, where a particle can leak through an energy barrier even if its energy is insufficient to overcome it classically, plays a key role in alpha decay, the emission of an alpha particle, consisting of 2 protons and 2 neutrons by a nucleus, and even more importantly, in the thermonuclear reactions that power the sun and stars. Further research showed that nucleons themselves, protons and neutrons, are not elementary, but are composed of even more fundamental particles or quarks. There are 6 flavors of quarks: up, down, strange, charm, bottom and top, which have fractional electric charge. In addition to electric charge, quarks carry another type of charge called color, conventionally red, blue and green. The strong interaction between quarks, which holds them inside nucleons, is described by quantum chromodynamics, QCD, and is mediated by the exchange of other carrier particles and gluons. Quarks, along with leptons, which include the electron, muon, tau lepton and 3 types of neutrinos, make up the so-called standard model of particle physics, an extremely successful theory that describes all known elementary particles and 3 of the 4 fundamental interactions: electromagnetic, weak, and strong. The great dream of theoretical physicists for many decades has been the creation of a unified theory that would unite all 4 fundamental interactions of nature. Quantum electrodynamics, QED, developed by Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga, describes the electromagnetic interaction as the exchange of virtual photons with incredible accuracy, after a clever mathematical procedure called renormalization, which made it possible to get rid of infinities in the calculations. In the late 1960s, Steven Weinberg, Abdus Salam and Sheldon Glashow successfully unified the electromagnetic and weak interactions into a single theory of the electroweak interaction. The next step is the creation of so-called grand unified theories, GUTS, which attempt to include the strong interaction in this scheme, often using the concept of supersymmetry, which suggests that every known fermion particle has a supersymmetric boson partner and vice versa. However, the most complex and fundamental interaction, gravity, which in the macroscopic world is described by Einstein's general theory of relativity as a result of the curvature of spacetime itself by mass and energy, has so far stubbornly resisted quantization and unification with the other forces. The search for a theory of everything that would harmoniously combine quantum mechanics and general relativity is the holy grail of modern fundamental physics. The leading candidates for this role today are considered to be string theory, or its more modern version, M-theory, which suggests that the fundamental objects are not point-like particles, but tiny one-dimensional vibrating strings, or multidimensional membranes existing in a space with more than 3 dimensions, and loop quantum gravity, which attempts to quantize space-time itself, representing it as a discrete network of loops on the so-called Planck scale, the fundamental scale of length, time, and energy, at which the quantum effects of gravity are expected to become dominant. Beyond these fundamental quests, the practical applications of quantum mechanics continue to change our world at an accelerating pace. Semiconductor technologies, based on an understanding of the band structure of solids, the behavior of electrons in the crystal lattice of silicon, doped with various impurities to create N-type and P-type materials, led to the invention of the transistor, then integrated circuits, and finally, the ubiquitous microchips that power our computers and gadgets. Lasers, whose operation is based on the principle of stimulated emission of coherent photons by atoms in an excited state, have found applications in countless fields, from medicine and industry to consumer electronics and communication systems. The phenomenon of superconductivity, the complete disappearance of electrical resistance in some materials at ultra-low temperatures, explained by the formation of Cooper pairs of electrons, which behave like collective bosons, allows for the creation of super-powerful electromagnets used in medical MRI scanners and scientific particle accelerators. Nuclear energy, both based on the fission of heavy nuclei and the promising thermonuclear energy based on the fusion of light nuclei, following the example of the Sun, are all direct consequences of our understanding of quantum processes in atomic nuclei. In medicine, in addition to MRI, which uses the phenomenon of nuclear magnetic resonance of the spins of atomic nuclei, positron emission tomography, PET scanners, is widely used, which utilizes radioactive isotopes that emit positrons, the antiparticles of electrons. The annihilation of these positrons with electrons in the body's tissues produces gamma rays that are registered by detectors, allowing for the creation of images of the metabolic activity of organs. Even complex biological processes like genetic mutations can have quantum effects at their core, for example, the tunneling of protons in a DNA molecule. The development of scanning tunneling microscopy, STM, and atomic force microscopy, AFM, has made it possible not only to perceive individual atoms on the surface of materials, but also to manipulate them, moving them with a sharp probe, which opens up fantastic prospects for nanotechnology, the creation of molecular machines and devices of atomic size. The recent discovery and study of Bose-Einstein condensates, macroscopic quantum states in which thousands or millions of ultra-cold boson atoms behave as a single coherent quantum wave, promises new breakthroughs, such as the creation of atom lasers, and that is far from the limit. Experiments with single atoms and photons, cooled to ultra-low temperatures with lasers and held in special traps, allow scientists to directly investigate and control such fundamental quantum phenomena as superposition, entanglement, and decoherence. These studies have already led to the emergence of a field like quantum cryptography, which offers methods for encrypting information whose security is guaranteed not by the complexity of mathematical problems, as in classical cryptography, but by the fundamental laws of quantum physics, for example, the impossibility of measuring a quantum state without disturbing it, or the properties of entangled particles. If it ever becomes possible to build a full-scale quantum computer, it could bring about a true revolution in many fields. A quantum computer will operate not with classical bits, which can only be in a state of 0 or 1, but with qubits, quantum systems, for example, the spins of electrons or atomic nuclei, the polarization of photons, that, thanks to the principle of superposition, can simultaneously be in states corresponding to both 0 and 1. By using the phenomenon of entanglement to connect many qubits, a quantum computer could perform a huge number of calculations in parallel, which would allow it to solve problems that are fundamentally inaccessible to the most powerful classical supercomputers. For example, quantum algorithms already exist, such as Shor's algorithm for factoring large numbers into prime factors, or Grover's algorithm for searching an unsorted database, that demonstrate an exponential or quadratic speedup compared to their classical counterparts. The main problem on the path to creating a practical quantum computer is the fight against decoherence, which tends to destroy the fragile quantum superpositions and entangled states due to interaction with the environment. However, researchers are actively developing methods of quantum error correction and are searching for ever more perfect ways to isolate qubits. And finally, quantum teleportation, a process that sounds like science fiction, but has already been experimentally demonstrated for individual photons and atoms. This is not the instantaneous movement of matter through space, but the transmission of the complete quantum state of one particle to another, located elsewhere, using entanglement and a classical communication channel, with the original particle inevitably being destroyed, losing its original state, in the process of teleportation. From the fundamental mystery of the two slits, which challenged our understanding of reality more than a century ago, to the stunning prospects of quantum computers and teleportation, the quantum world continues to surprise, inspire, and promise new, even more incredible revolutions in science and technology. It remains strange, paradoxical, often counterintuitive, but it is the fundamental reality upon which our world is built. And our journey into its depths, our mastery of its limitless possibilities, is only just beginning. The future, without any doubt, belongs to the quantum.